So welcome to this short revision video on using absorption and emission of photons from atoms for spectroscopy, and the same procedure is used for the technique of colorimetry. So remember, every atom will absorb radiation at a very specific set of wavelengths, and it will also emit photons at the same specific set of wavelengths. This is dependent on whether or not the electrons are being promoted, that is when it will absorb radiation, or whether the electrons are falling back down to lower energy levels, that is when it will emit radiation. So in an emission spectrum, you will see a few specific coloured lines, whereas in an absorption spectrum, the atom will have gaps of no colour for where the radiation has been absorbed. The rest of that radiation has passed through the sample. Now, in absorption spectroscopy, this is when we are looking at radiation that has been absorbed by a sample to promote electrons. We take our electromagnetic radiation, and this is typically visible light or ultraviolet, but could honestly be any of the types of electromagnetic radiation, and we fire it at an atomized sample. Atomized means that it has been completely destroyed, no longer exists as a compound, no longer exists as molecules. Every single atom has been broken, there are no bonds. And that can be done using chemical means or sometimes using alternative energy to destroy the sample into atoms. Radiation from the electromagnetic spectrum will be absorbed as electrons are promoted to higher energy levels. And the absorption spectrum shows how the intensity of absorption varies with wavelength. So, for example, a particular atom might absorb the colour red, whereas another atom might absorb the colour blue. Or even within one atom, it might absorb loads of red, a little bit of green, a little bit of blue, but there will be a specific pattern. When you're wanting to measure the concentration of a sample, you're always going to use whatever wavelength is the most absorbed by the sample. In emission spectroscopy, we need to excite the atoms as well as make our measurements. So we atomize our sample, but then we also use really high temperatures to excite the electrons. Remember, it's not just photons that can excite an atom, it can be electricity, it can be heat, potentially sound, but that would be less common. It's usually going to be a high temperature. So we've excited the electrons, they're at higher energy levels than normal. As they fall down to their lower energy levels, you will release photons of different wavelengths. And you can measure the intensity of light given out by the sample across all the different wavelengths that you are recording. And if you're wanting to measure the concentration of a particular atom using emission spectroscopy, you're going to be looking for which wavelength of light gives the most intense emission response. So how do we use absorption emission spectroscopy? Together, this is known as atomic spectroscopy. And you can either measure the absorption or emission spectroscopy for a sample. Each type of atom will have characteristic wavelengths where it absorbs and emits. The intensity of wavelengths relates to how many of a particular type of atom is in the sample. So for example, if you were potassium and you're doing a flame test, if you had one atom of potassium, you might not even register a purple colour, that lilac flame. But if you then had like 1 milligram of sample, you'll be able to see the purple colour. If you had 10 milligrams, the purple colour will be even stronger. The intensity of the colour emitted or absorbed depends on how many of a particular atom you have. And so If you're measuring at one particular wavelength, you can actually correlate the intensity, how strong the absorption or the emission is, to a concentration of a sample. And this technique is so specific and so good that we can measure quantities in the parts per billion or parts per trillion. So that is one atom out of a trillion atoms you would be able to measure its concentration. And this is a really important technique used for measuring trace impurities within a sample. Some companies will actually label their goods with specific atoms so that you can then measure the absorption and check that it is exactly what it was supposed to be. And it's also used for forensic analysis and anthropology analysis, so analysing bones and teeth to see where they came from and what lifestyle they had. Now, in this technique, what you need to know is the absorption or emission is related to the concentration of atoms in that sample. And remember, you're always atomizing the sample, because if you've got bonds, that's going to interfere with the degree of absorption or emission. We can work out the concentration of a particular atom within an unknown sample by comparing its absorption to a set of known samples. So what we need to create is something called a calibration graph or a calibration curve. So there are a few steps to making a calibration graph. The first thing is that you need to make a set of standard solutions. Remember, standard solution, accurately known concentration, containing the element, or in the case of colorimetry, compound you want to investigate. And you need at least 5 different concentrations for a good calibration graph. In the machine, your absorption or emission machine, you need to measure a blank sample. That blank sample is just the pure solvent that you've used to make your standard solutions. The reason you need to do that is because there are atoms within any solvent, and those atoms will absorb at specific wavelengths. So this blank allows you to remove the background from the solvent. You've measured it, so you can subtract that, or the machine will automatically subtract that from all your future measurements. You then take each of your solutions, each of your standard solutions, and you measure either the absorption or the transmission. Absorption is what is absorbed, transmission is what passes through it, for each of your standard solutions. And you can then plot the intensity. And you draw a graph, concentration along the bottom and your absorption or transmission or intensity on the y-axis. And you need to get a straight line. If you do not get a straight line, something has gone wrong either with the machine or with your standard solutions. You cannot use a calibration graph if it is not a perfect straight line. And your straight line can only go through the points that you have plotted. Do not make it go through the origin. Do not extrapolate it beyond your highest concentration. You just want it to fit perfect straight line from your lowest solution to your highest solution. Now, once your graph is ready and it is straight, you then take your sample where you do not know the concentration and you measure the emission or the transmission of your sample, and you get the intensity of that. You then read up on your scale for the intensity, the absorption, the emission, the transmission, read along to your line of best fit, and then read down to what the concentration is. An issue can sometimes be that you measure your sample and you get an intensity or an absorption that is higher than you had on your calibration graph. If that's the case, you need to dilute your sample so that it fits on the calibration curve. But then remember, if you've diluted your sample, that whatever concentration you get, you're going to need to scale up based on how much you diluted it by. So this is what your typical calibration might look like. You then, your concentration can be any measurement of concentration. It doesn't have to be moles per litre. It can be mass per litre. You measure the absorbance of your sample, you read across to the calibration graph, and then you read down to the concentration. Remember, if you needed to dilute your sample in order to fit it on the calibration graph, to then scale up your concentration based on whatever dilution factor you had. So this was how to use emission and absorption spectroscopy and how to do a calibration graph. The details for how to do a calibration graph and then how to measure your sample is important. It often comes up as two individual questions. How do you prepare your calibration graph? Then how do you use your sample to measure concentration? Know that, and it is guaranteed to come up.